I'd like to talk about surface forces in this lesson, and I've sketched here a force separation curve taken with a stiff cantilever that for the first time is different loading and unloading. And they differ because, in fact, the surfaces have come into contact. So some vocabulary here. When I refer to surface forces, I'm referring to whatever long-ranged forces act between the tip and the sample as you're bringing them together. This part of the curve here. When I'm talking about adhesion, I am referring to the unloading curve, and so I am referring to what's going on down here. And adhesion, you've been in contact. It's possible that some of the atoms on the tip have chemically bound themselves to some of the atoms on the sample. So I think of adhesion as whatever long-ranged surface forces there are, plus any bonding that's going on during the contact phase. So if I had more room there, I would say bonding during contact. I've drawn the surface forces as attractive, that is, the cantilever is bending towards the sample during the loading process. However, that's not always true. It is possible to have repulsive forces, although that's less common. I group surface forces into 4 classes: electrostatic, electrodynamic, electromagnetic, and liquid films. By electrostatic, I mean there might be charge accumulation on one or both surfaces, or you can coat the tip and sample with metal and apply voltages to them. So if you remember from intro electricity and magnetism, there is energy stored within the plates of a capacitor, and that's more or less what you have when you have a tip and a sample separated by some space. You've got energy stored in the electric field there, and there are forces associated with that. By electrodynamic, I mean the fluctuating motions of electrons, and this leads to van der Waals forces. Or if you've got a liquid that has polar molecules in it, those molecules can rotate around and also give rise to changing electric fields. Electromagnetic, think of your hard drive, how the bits are stored magnetically. Well, you can magnetize an AFM tip and do magnetic force microscopy and visualize the bits in a hard disk, even though the topography of the surface is pretty flat. And finally, liquid films. Well, lots of liquids have surface tension. Think of insects on water. They're able to walk on water because the surface tension keeps them up. And this can affect force curves as well. I'm going to treat 2 of these classes of surface forces very perfunctorily, and then we'll go into more detail on the other 2. The 2 that I'm just going to summarize in a few words here are the electromagnetic forces. Magnetism is a tough subject. I probably still don't understand it, and so we're not going to attempt to give you a nice simple explanation of it when I feel as if I don't really understand it myself. So I will say, though, that there's some very nice images of magnetic bits on hard drives out in the literature, and I encourage you to go look for them if this is a topic of interest for you. The data acquisition is done in AC mode, dynamic mode, such that you're talking about the longer ranged interaction between the magnetized AFM tip and the bits in the hard drive. So that is that. For electrostatic forces, if you're applying a voltage to metallized tip and metallized sample, that is fairly straightforward, but the confounding situation is fairly common of getting charges on insulators. If your sample is an insulator and your cantilever is an insulator, then charges can build up on those surfaces just in the same kind of process as you're dragging your feet across the carpet in the wintertime. It's dry, you build up charge, and then you go and you shock your friend. Well, just as you don't know how much you're going to shock your friend when you start off, you don't count the number of steps or anything, you're never quite sure how much charge you build up. Likewise, in AFM, you're never quite sure what charges are doing. That can lead to some very puzzling motions of the cantilever. So as much as possible, try to use conducting surfaces, or move the system inside water. Water is not a bad conductor and can allow charges to move around and equilibrate. I will talk about van der Waals forces and liquid films, however, because those are the two most common types of forces that you're likely to encounter. Now, given the amount of time left in this lesson, I'll do the shorter of the two topics, and that is that of liquid films. As you work around your kitchen, you've probably noticed some surfaces on which water will flatten out, and on other surfaces it beads up. We use the terms hydrophilic and hydrophobic to describe this behavior. The roots are hydro for water, philic means friend, and phobic you can think of as foe. In other words, water likes hydrophilic surfaces and doesn't like hydrophobic surfaces. What is the mechanism by which this happens? So you might know that water molecules have an oxygen and two hydrogens, and oxygen is like electronegative, which means it pulls electrons towards it, making this end of the molecule positive and kind of leaving the protons of the hydrogen exposed. So that's a little dipole. A dipole being something with positive and negative charges associated with it, separated by a distance. And the dipoles, the water molecules, are rotating around in liquid form, and they like to stick together because they have these dipole moments which interact with each other and are attractive. So if a surface also has dipoles in it, however they might be arranged, the water likes that and spreads out so as to interact with as many of them as possible. A hydrophobic surface will not have as many polar dipole moments in it, and so the water molecules are quite happy to stay in solution, and they want to minimize the area of contact with hydrophobic surface because they prefer to be with themselves rather than interact with the surface. So let's say that it's a hot, humid day in the lab. Your tip and sample are hydrophilic enough such that a thin uniform layer of water has condensed on it. So think of a cold can of soda on a hot, humid day. And we're going to bring the tip and sample close to each other and think about how that thin film of water behaves. Here I've redrawn it with the tip just a little bit closer to the sample and the water films on both tip and sample. And what I want you to notice is that there's a bunch of area right here, the surface of the water, and as soon as the water films touch, those water molecules are going to say, oh, new friends, and they're going to try and get us rid of much area of the surface of the water as possible, because water molecules don't particularly care for air. They prefer each other. So the new profile of the water will be more like this. So we have formed a meniscus right at the interface between the tip and the sample, and that is minimizing the area of the water that is exposed to the air. And the formation of that meniscus, water surface tension is pretty small, pretty strong. That's going to pull the tip down suddenly towards the sample. Let me show you what that looks like on a force separation plot. Here we're approaching tip and sample. Cantilever starts to bend forward due to attractive forces, say van der Waals. And then suddenly, right here, we've got the meniscus formation. Then you load up the sample, you unload it, and what's happening in this part, well, after you have formed the meniscus, you are now drawing that fluid apart, you're elongating it, and you're forming a liquid bridge between the tip and the sample. And you can also call this capillary, reminiscent of the capillaries in your blood circulation system. And remember that water does not like lots of area. It likes itself. It does not like to expose itself to air. And so it costs energy to form this capillary. And that's why down in the bottom here on the unloading, that trace is below where it was on the loading, because that position refers to more energy in the cantilever. And when the capillary breaks, as it does because of some jostling or whatnot, then there's a little jump right here. And what I find interesting is that the difference between approach and retraction, that's an area on a force displacement plot or force separation plot, that area corresponds to energy. So the energy in that area, that corresponds to the amount of energy it takes to pull the capillary out and then have it break. Where does that energy go? It goes into the water sloshing around on the capillary, on the tip and on the sample, making little waves on the tip and the sample, and that's a dissipative function, meaning we have lost energy in the sense we've changed it into a form that is not particularly useful to us. In summary, in this lesson, I said a few brief words about electrostatic and electromagnetic forces, and spent some more time on liquid films, and in the next lesson we'll talk about electrodynamic forces, van der Waals.